All right, starting with the first problem here, it says find the general solution of the differential equation. So remember, all of these equations are derivatives. They all say f prime, but they could also say dy dx. But the general solution to the f prime equation is find the f of x equation, and it'll be equal to something plus c. All right, so, and that's because the integral of f prime of x dx is equal to f of x plus c. All right, so I need to take the integral of 1 minus 6x dx. So remember your integration rules. The integral of a constant is x, so this is 1 times x. The integral of x to the first is x squared over 2, so minus 6x squared over 2 plus c, and then we just clean this up a bit. So the general solution is f of x equals x minus 3x squared plus c. You can change the order of that if you don't like having this not in standard form, but I'll just leave mine like that. All right, so I want to take the integral of 3 cosine x plus 5x squared dx. So the integral of cosine, remember when you're thinking of trig integrals, it's always like cosine is the derivative of what? So the integral of cosine is sine, and so this will be 3 sine x. You can always double check quickly in your head, just like take the derivative of what you just wrote down. Derivative of 3 sine is 3 cosine, so you're good. And then this becomes plus 5x to the third over 3 plus c, and that's equal to f of x. For the next one, remember you can rewrite roots as exponents. It's usually easier to look at. So this is the same as x to the 4/5. So that's f prime. So we want to take the integral of 1 plus x to the 4/5 dx. Make sure you're setting these integrals up correctly, by the way. You need parentheses around the expression if it's more than one term. You need to have dx here. If you just have the integral of the expression, you technically wouldn't get credit for writing the integrand. Anyway, integral of 1 becomes x plus add 1 to 4/5, so add 5/5, you get 9/5, so x to the 9/5 divided by that new exponent plus c, and I'm going to rewrite that. So that's x plus, instead of dividing by 9/5, we will multiply by 5/9, still times x to the 9/5 plus c. All right. Next problem says find f. So instead of the general solution, sometimes they call this the particular solution. So they want us to figure out what is the specific plus c that you need to have in order to achieve whatever function value they're telling you. So you start off the same way. We're going to start off by saying, well, f of x is equal to the integral of 8x cubed plus 12x plus 3 dx. Okay, so what does that get me? So that gets me 8x to the 4th over 4 plus 12x squared over 2 plus 3x plus c. So cleaning that up, that tells me that, I'm going to put my work over here. So that tells me that f of x is equal to, this is 2x to the 4th plus 6x squared plus 3x plus c. Now apply this condition that they've given you. So f of x is equal to 6 when you have an input of 1. And that will allow us to solve for the constant of integration for c. So 2 plus 6 is 8, plus 3 is 11. Excuse me. So solve for c, you get negative 5. Okay, so final answer, what is f? So now I know, okay, f of x, I don't really know where to write this. I'm going to put it down here. So f of x is equal to 2x to the 4th plus 6x squared plus 3x minus 5. All right. Let's see. So for the next one, same idea. So we're going to integrate to begin with. So if I integrate 5 sine x plus 3 cosine x dx, I get, so the integral of 5 sine x will be negative 5 cosine x. And again, if you think you're going to mix up the negatives, there are two ways to remember it. If the integral starts with a c, if the answer to the integral starts with a c, you're going to get a negative. Or I just usually in my head go back and say, okay, wait, the derivative of negative cosine is positive sine. So I do a quick check mentally. The integral of 3 cosine x is plus 3 sine x plus c. So that's my f of x equation. So now I can say that, solve for c. So I can say that 4 is equal to negative 5 cosine of 0 plus 3 sine of 0 plus c. I would suggest plugging the angle in before you do the trig so that you don't mix up your numbers. So cosine of 0 is 1. Sine of 0 is 0. So this is going to tell me that c equals 9. And then that means that f of x is equal to negative 5 cosine x plus 3 sine x plus 9. All right, for this one, for part C, you're given the second derivative, and then you're given function values for both f of x, f of 1, and f prime of 1. So remember, when we integrate the second derivative, we're going to be left with the first derivative equation. So I'm going to begin by taking the integral of 20x to the third minus 10 dx. So that gives me 20x to the fourth over 4 minus 10x plus c. And remember, this is the f prime equation. So this tells me that f prime of x is equal to 5x to the fourth minus 10x plus c. So I want to use this f prime information to say f prime is negative 5 when has an output of negative 5 when I have an input of positive 1. 5 minus 10 is negative 5. Add 5 to this side, you're going to get c equals 0. All right, so f prime of x is equal to 5x to the fourth minus 10x plus 0. Now we need to integrate again. So I feel like I'm going to do an arrow here. So now I want to integrate f prime so that I get f of x. So 5x to the fourth minus 10x dx. So that's equal to 5x to the fifth divided by 5 minus 10x squared divided by 2 plus c. So this is my f of x equation. So f of x is equal to x to the fifth minus 5x squared plus c. And now I can plug in this condition where when you input 1, your output is 1. So 1 equals 1 minus 5 plus c. This is negative 4, so if I add 4 to the side, I get that c equals 5. So f of x is equal to x to the fifth minus 5x squared plus 5. And the nice thing about these is you can check your answers because I can find, based on this f of x, what is the second derivative equation, and I can see if I get this f double prime of x. So you can kind of check. Evaluate the indefinite integrals. So evaluating an indefinite integral just means that your answer will be something plus c. All right, so this is already set up for me, so there's nothing to rewrite. I can say this is 5x to the fifth over 5 minus 2x squared over 2 plus 3x plus c. And now I just need to clean it up. So x to the fifth minus, no 2 there. The 5's cancel, the 2's cancel, so x to the fifth minus x squared plus 3x plus c. We don't have information to find c. This is just what we get when we evaluate an indefinite integral. All right, remember we cannot take, here's an illegal thing. It's illegal to say I'm going to take the integral of the top over the integral of the bottom. This is illegal math, terrible, don't do that. What you should do is divide. Remember, we can always, if there's a single term in a denominator, the first thought is to divide that away. So let's rewrite the problem before we integrate it. 6x to the fifth divided by x squared is 6x to the third minus x cubed over x squared, so minus x. Now I can just use my little power rule for integrals. So I get 6x to the fourth over 4 minus x squared over 2 plus c. And then I clean that up. 6 over 4 reduces to 3 over 2. X to the fourth. Nothing else to simplify. And I guess, you don't have to simplify the fractions, but when we apply these skills to our AP test, the problems are not usually just find this integral. It's find this integral and do something with it, set it equal to something, plug something into it. So that's the point of reducing simple things like 6 over 4. All right, what about these? Again, it's illegal to say integral of the top over integral of the bottom. These should be jumping out to you as Pythagorean identities, but if they're not, here is the Pythagorean identity that you still have to know. Sine squared theta plus cosine squared theta is equal to 1. And remember, we had rearranged versions of this. If you solve this for either one of the terms, sine squared is equal to 1 minus cosine squared. Cosine squared is equal to 1 minus sine squared. So we can make some substitutions here and say this is the integral of 1 minus cosine squared is sine squared theta. On the bottom, 1 minus sine squared theta is cosine squared theta. And that gives me the integral of tangent squared. That gets me somewhere, right? But I'm actually not finished here because tangent squared, that's not, when you're dealing with trig, it's like, what is this the derivative of? And tangent squared is not the derivative of anything. So we have to think about this some more. All right, well, what else can we do? We can say that tangent squared, sorry, I'm putting lotion on my hands. Okay, we can say that tangent squared is, here's another Pythagorean identity for you. Tangent squared theta plus 1 is equal to secant squared theta. All right, so what does that mean? Well, if I have tangent squared theta, I could replace that with secant squared theta minus 1. Does that help me? This does help me because secant squared is the derivative of something. It's the derivative of tangent, and I can integrate 1. So this helps me by saying integral of secant squared is tangent theta. The integral of 1 with respect to theta will be minus theta, and then we'll have plus c. And this is not the only way to do this. This is the way I would think to do it. But you could also have said, let's work on this integral. 1 minus cosine squared theta over cosine squared theta. The bottom, I just replaced the bottom. And then you can Hart method. See how I get to the same place? Secant squared theta minus 1. Okay, so you could do that too. You would still get to this place. All right. On to the back page. Given f of x is equal to 5 over x on the interval 2 to 5, find a lower sum with 3 equal subintervals. So you need to sketch this graph on this interval because the lower sum, I don't know right now off the top of my head if that's the left sum or the right sum. I need to know, is the function increasing on this interval or decreasing? So sketch the graph. You're just plugging 2 points into it. You don't have to go crazy. So here's 2. If I plug 2 in, I get 5 over 2. If I plug 5 in, I get 5 over 5. So this is 2.5. Let me adjust this so it's not such a tiny graph. So here's I'm just going to say 2.5 is up here, 5 over 2. And then when I plug in 5, I get 1. Again, the scale really doesn't matter. This is a rational graph, so I know I'm on one of the branches here. So I know it's curved like that. But again, that's not really too relevant as far as you just want to have a good idea of is this increasing or decreasing. So the curvature does not really matter in my sketch. All right, so this is a decreasing function. I want to find delta x first. Remember, the formula for delta x is b minus a over the number of subintervals, so 3. 3 over 3 is 1. So when I divide this into 3 equal subintervals, they're all 1 unit apart. So 2, 3, 4, 5. All right, now what is the lower sum going to be? So this is a decreasing function. I want the rectangles to stay underneath the curve. So looking at my picture, that's going to have to be a right sum, where you use the right corner of the triangle to touch the function, and that indicates the height. So in this case, a lower sum is a right sum. Excuse me, if f of x were increasing, a lower sum would have been a left sum. Okay, so now we can set up our integral. So we're estimating a value for the integral from 2 to 5 of 5 over x dx. We're saying that's about equal to this delta x, which is 1, times the height of each function, because this is just the area of each triangle. So the first height is f of 3 plus f of 4 plus f of 5. All right. I know that we mostly use a calculator. We will eventually have a short quiz over this where we don't use a calculator, so just practice without too. This function is not bad to type into or to do by hand. So this would be 5 over 3 plus 5 over 4 plus 5 over 5. Like I said, we can do this without, hopefully we can still do this without a calculator. The common denominator is 12, and I would be saying, actually I'll do the work over here. Common denominator is 12. This would be 20 plus 15 plus 12 to get those common denominators all set up. So let's see, this is 35 plus 10 is 45 plus 2 is 47. If you do want a decimal approximation, 47 over 12, 3.917. Okay, find a midpoint sum with 3 equal subintervals. So it's still the same thing, but I'm going to draw the picture again, just so I have a fresh picture to map onto. All right, so we have something like this. Our delta x is still 1 unit, so 3, 4, 5. And then the midpoint sum is saying, okay, halfway between 2 and 3, you'll put a point on the function and you'll draw a little rectangle like this. Part of the rectangle is falling short of the curve and part is hanging outside. It's not always the same exact amount because of the curvature of the function, but it's kind of close. And then at 3.5, I'll do that. And at 4.5, I'll do that. And so this is the area that we're looking for here. All right, so this one is saying the integral from 2 to 5 of 5 over x dx could be approximated by 1, which is the delta x, times the height of each rectangle. So f of 5 over 2 plus f of 3.5, so 7 over 2, plus f of 4.5, so 9 over 2. All right, I guess I am going to use a calculator for these. Again, it's not that they wouldn't have us do this. It's not that they wouldn't have us do this as a non-calculator problem, but it's just faster. It's 6:48 in the morning, might as well. Okay, so 1 times f of 5 over 2 plus f of 7 over 2 plus f of 9 over 2. 4.540. It's nice to have the decimal version too, because you can say, yeah, this should be larger than the lower sum, because even though you're still leaving some area out, you're kind of accounting for that by putting in some extra area on the outside as well. Evaluate the Riemann sum for f of x equals radical x plus 2 on 0 to 9 with 5 equal subintervals. Use right endpoints. So this time it doesn't say an upper or a lower. I'm still going to sketch the graph here. And this says round to 3 decimal places. So again, we will use a calculator. So when you plug in 0, square root of 0 plus 2 is 2. When you plug in 9, square root of 9 is 3 plus 2, it's 5. I know that a square root graph has sort of a curve like that. We want 5 equal subintervals, so the first thing to do is calculate delta x. So it's 9 minus 0 over 5. 5 equal subintervals, so 9 over 5. All right, so that's kind of an ugly way to divvy things up. But if you're just doing 5 equal parts, I'm going to do my best to sketch this in. 1, 2, 3, 4, right? 1, 2, 3, 4, 5 equal subintervals. Just count by 9/5. Like from 0 to 9/5 is 9/5. 18 over 5, 27 over 5, 36 over 5, 45 over 5 would be 9. So there's that. This is why we're using a calculator. All right, so we're saying that the integral from 0 to 9 of the square root of x plus 2 dx can be approximated by a step size or a delta x of 9/5. Every rectangle has that base. And if we're using the right endpoints, I didn't draw that in, start on the right side of the interval. And so this would be an upper sum because this is an increasing function, so the right endpoints are going to be outside of the graph. All right, so the first height of the first rectangle is f of 9 over 5 plus f of 18 over 5 plus f of 27 over 5, plus f of, what did I miss? 1, 2, oh no, I didn't miss anything, sorry. 36 over 5 plus f of 9. If you have 5 equal subintervals, you should have 5 function heights here because there are 5 rectangles, right? Every function height that you write in represents the height of the rectangle that you're adding in. All right, so this is another one where let's put this equation into the y equals, so square root of x. Make sure the plus 2 is outside of the square root. And then you've got 9/5 times the quantity. Alpha trace gives me y1 of 9 over 5 plus y1 of 18 over 5 plus y1 of 27 over 5 plus y1 of 36 over 5 plus y1 of 9. It's important that you're not finding these values separately and rounding their decimals and then using rounded values to calculate because your answer will be not as accurate as it should be, and that it needs to be accurate to 3 decimal places for the AP test. So 38.243. Does the sum represent a lower or upper sum? So I like to have the picture to decide this because the function is increasing and we used a right endpoint, this is an upper sum. So upper sum, is this an underestimate or overestimate of the actual area? So this is an overestimate, right? I can see that. That's what upper sum means. Upper sum, overestimate. It doesn't ask to explain, but the explanation would be because f is increasing, the right sum is the upper sum, and an upper sum is an overestimate. Given y squared minus 2, approximate the area bounded by the function, the x-axis, x equals 3 and x equals 6. Use a trapezoidal sum with 3 equal subintervals. So let's graph this thing first. So let's see, we're going from 3 to 6. When you plug 3 in, you get 9 minus 2 is 7. When you plug 6 in, you get 36 minus 2 is 34. I'm not worried about scale here, right? So it's just this point to this point. I know this is a parabola, so it's got a curve like that. Use 3 equal subintervals. So delta x is 6 minus 3 divided by 3. 3 divided by 3 is 1. Okay, so I'm just going to kind of divvy this into 3 spots and count by ones. And we're supposed to use trapezoidal. So remember, that means that you put points at every section here, connect those points with a little line segment, and the trapezoid you're looking at then would be using the parallel sides that are the function heights here. So this one is the integral from 3 to 6 of x squared minus 2 dx can be approximated by delta x is 1. Okay, oh wait, sorry. Remember the area of a trapezoid. Let me remind you of this. It's 1/2 the height, so height over 2, times b1 plus b2. And then remember, the height is really the delta x. And then the b1 and b2 will be f of x1 plus f of x2. And you'll just keep going from there. So instead of me saying just 1, delta x was 1, they're all going to have this 1/2. So let's just pull that out in front. Okay, so then we get f of 3 plus f of 4. That's the sum of the first two bases. So there's the first trapezoid. Plus the next trapezoid uses f of 4 plus f of 5. Plus the third trapezoid uses f of 5 and f of 6. And it will always be this way. So you could condense this so you don't have as much to write. If you recognize that, like, oh yeah, these middle ones are always going to get doubled, the endpoints will only show up once, you could skip right to saying this. I usually do this just so I have less to write out or less to type in instead of writing what I originally wrote. But it doesn't matter. Okay, and then let's go ahead and we'll just keep with our theme of using our calculator. So x squared minus 2. And I've got 1/2 outside of parentheses. And so that was y1 of, I need to split screen here. There we go. So y1 of 3, 3, plus 2 times y1 of 4, plus 2 times y1 of 5, plus y1 of 6. 57.5. All right, let's take a look at number 7. Find this integral using the limit of Riemann sum. So this is the long one, right? So in other words, find the exact area on 2 to 3. So this is like our limit definition for a Riemann sum. All right, so we should still graph this thing. I like to do that. So we're going from 2 to 3. When you plug in 2, you get 8. When you plug in 3, you get 13. Again, I just kind of like having the visual. You don't necessarily have to graph this. All right, so what's our formula for delta x? Our formula for delta x is that we're going from A to B. So we're going from 3 minus 2 over n subintervals. So that's 1 over n. And then remember, we could start the first rectangle anywhere we want. It could be right here. And then from that, we build off of that. So we need to write an expression for f of x sub I. So f of x is normally something squared plus 4, right? X squared plus 4. In our spot, we're going to say, well, our first rectangle could be starting at 2. I could add any number of delta x times i's, and that would land me at my first spot. So this is just saying, like, this spot here is 2 plus some number of delta x's times I. We have a formula for delta x. It's 1 over n. So really this is 2 plus I over n squared plus 4. And remember, with this, it's good to do the math and get this all squared out without parentheses down here. so you don't have to keep rewriting summations and integrals. So clean this up as much as you can. Square the binomial. 2 squared is 4. 2 times 1 over n is 2. 2 times I over n is 2i over n. You're going to double that, so 4i over n plus I squared over n squared plus 4. Clean that up a bit more. 8 plus 4 over n times I plus 1 over n squared times I squared. You don't have to separate it out like that. I just kind of like to do that. And so what we're saying is the integral from 2 to 3 of x squared plus 4 dx is equal to the limit as n approaches infinity of the sum from I equals 1 to n of delta x times f of x sub I. And actually, just so I don't have to write all this again, I'm going to write that up here. Delta x times f of x sub I. I just spent the work going through that. So delta x is 1 over n, and f of x sub I is 8 plus 4i over n plus I squared over n squared. So I'm going to distribute the 1 over n, and then I'll go ahead and do my summation stuff. You don't have to do that. You can do it all at once if you want, but I just like doing it this way. So this is 8 over n plus 4 over n squared times I plus I squared over n to the third. So the next step is to, once you get this set up, get rid of the summation symbol by saying what these are going to add up to. So keep the limit as n approaches infinity. Okay, and then what are our rules? So if you need to have your notes out, you can have your notes out for this, but using your abstract, using this. So when you have a constant, the sum, when you get rid of the sum, it'll be n times the constant. Okay, so make sure I'm on the right one here. So 8 over n times n. And then I have plus 4 over n squared. And again, you can look back at your notes if you want to, but the sum from 1 to n of I will be n times n plus 1 over 2. And then I've got a 1 over n to the third. And the sum of I squared, I believe that's n times n plus 1 times 2n plus 1 all over 6. I'm going to double check that because it's early and I could be making a mistake. What did I say? I squared, n times n plus 1 times 2n plus 1 over 6. I did it right. Okay, and then now we're looking at a limit at infinity, which we did back in like chapter 1, right? So this was saying, okay, what's the limit as we approach infinity? Well, here the n's cancel out, so that first limit is 8. Here we have a 4n squared over a 2n squared, so plus 2. And here we have a 2n to the third on top over a 6n to the third, so plus 1/3. So 10 and a third, or 31 over 3. That's our, it's not our approximation. That is the exact area between this curve and the x-axis. Okay. Sorry, let me clean this up a bit. I started to write 4x and then okay, there we go. All right, I'm going to stop after this problem because I have a meeting in a couple of minutes. So let d of t be the rate of growth of the deer population in Ohio at time t. Using the table, approximate the integral from 0 to 6 using a midpoint Riemann sum. Oops, I lost my pen here. With 3 equal subintervals and include units. All right, so midpoint, 3 equal subintervals. Start with delta t, figure out what that is. So that's 6 minus 0 over 3. So I should be going every 2 units. So if I'm marking this off, sometimes people get confused by this when it's a table. So if you're marking off every 2, that's just going to be 2, 4, 6, right? So 0 to 2, 2 to 4, 4 to 6. The midpoint, though, that you're going to use is 1, 3, and 5. So sometimes it helps to put it on your axis like this. All right, so the integral from 0 to 6 of dt dt is about equal to, so the delta t is 2, And then we're using the function height. So like I said, I'm going to use the odd numbers. So d of 1 is the midpoint of the first rectangle, plus d of 3, plus d of 5. And we get those numbers from the table. So d of 1 is 3 plus 8 plus 17. That's 2 times 28. And that would be 56. What is my label here? So we just multiplied thousands of deer per year times years. So we're left with 56,000 deer. That's our approximation. Interpret the meaning of this. So I guess I just did it here. So this is the represents the total deer population. Sometimes I say, instead of total, sometimes I say net change. This function would not dip below the x-axis, but if it ever did, it's the net change in deer population over 6 years, right? From year 0 to year 6. And it represents the deer population in thousands over 6 years. All right, I'm going to stop there. The last part of the video will be linked in a second video.